Video, I am going to explain basic thermodynamic cycles. In this video consists of Carnot cycle, Otto cycle, Diesel cycle, Brayton cycle, Stirling cycle, and Ericsson cycle. Here is my introduction. I am Rohan Gyaneshwar Salonke. My PRN is ME54. I am final year BTech Mechanical Engineering student. Then thermodynamic cycles. Then first is Carnot cycle, which provides theoretical limit for the maximum efficiency of the heat engine. Then there is the Otto cycle, which is commonly used in gasoline engines. Then diesel cycle is commonly used in diesel engines. Then Brayton cycle, commonly used in gas turbines, and the Stirling is a closed cycle engine that can operate in any external heat source. And then we'll move to our first cycle, which is the Carnot cycle. As I mentioned before, the Carnot cycle is theoretical thermodynamic cycle that often used as a benchmark for maximum possible efficiency for any heat engine. It consists of four reversible processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The significance of the Carnot cycle is lies in the fact that it sets a upper limit on the efficiency of the heat engine. This means that no real world heat engines can more efficient than the Carnot cycle engine. Here we can see the PV diagram and TS diagram for the Carnot cycle. Yeah, from the TS diagram, we clearly see that two processes are the isothermal processes, where they are the heat addition and the heat rejection processes, and the two processes are isentropic and isentropic processes, where one is the compression and another one is expansion. Now let's move to next cycle. In this cycle is Otto, which is proposed by N.A. Otto in 1876. So Otto cycle is a thermodynamic cycle that describes the functioning of spark ignition engine, such as those found in most of the cars. The cycle consists of four processes: intake, compression, power, and exhaust. During the during the intake process, air and fuel are drawn into the engine cylinder. The piston then compresses and the mixture during compression process. Then next, spark ignites the mixture and causing the huge expansion of the mixture, which moves the piston. And here's the power generated. So Otto cycle is named after Nicholas Otto, who is invented the four-stroke internal combustion engine in 1876. Since then, the Otto cycle has been refined and improved upon, leading the efficient, reliable engine we use today. Here, as Carnot engine in Carnot cycle, we have seen the TS diagram and PV diagram. Similarly, here we can see here we see two similar processes like isentropic processes, isentropic compression and expansion. But the other two, heat addition and heat rejection processes, are changed. They are not isothermal processes. Here they are isochoric processes, means they are constant volume processes. Here is the major difference between the Carnot cycle and the Otto cycle. Now moving towards our next cycle is the diesel cycle. As the name suggests, it is used in diesel. It is proposed by Rudolf Diesel in 1890. Diesel cycle is a thermodynamic cycle used in diesel engine, as I mentioned before. Unlike the Otto cycle, it which uses spark ignition, it does not require spark ignition. The air is compressed at least more than the air compressed in the Otto cycle, and in directly in the compressed air, the fuel is inject, in, injected, and that the high pressure leads to ignition, self ignition of that fuel, and thus it expands and we get the proper work output. The one of the key difference between Otto cycle and diesel cycle which is the fuel is ignited, self-ignited. In the Otto cycle, fuel is mixed with air and ignited with the spark plugs. But in the diesel cycle, fuel is injected directly into the cylinder and compressed until it ignites spontaneously. So here in the TS diagram, we can see the similarly as the Carnot cycle, two processes are the isentropic processes, but heat addition process is the isobaric process instead of isothermal or isochoric. But as similar to Otto cycle, the heat rejection process is the isochoric process. Then moving towards our next cycle is the Breton cycle. Breton cycle is proposed by George Breton in 1870. Breton cycle, also known as the Joule cycle, is the thermodynamic cycle that commonly used in a gas turbines. It consists of four processes: compression, heating, expansion, and cooling. During the compression process, air is compressed to the high pressure and temperature. This pressure air then heated by the burning fuel in the combustion chamber. The hot and high heated burning fuel in the combustion chamber, the hot high pressure gas is then expanded through the turbine, which converts the thermal energy into mechanical energy, and we get proper work output. The Breton cycle is widely used in gas turbines because it is highly efficient and can generate large amount of power. In um, in TS diagram, we can see the two processes, isentropic processes, are the same as the Carnot cycle, but in heat addition and heat rejection processes are the difference. They both, as we can see in Otto cycle, they both are isochoric processes. In diesel cycle, we have seen one is the isobaric process and one is the isochoric process. But here, both the processes are the isobaric processes. Now, moving towards our next cycles are the Stirling and Ericsson cycle. The Stirling cycle and Ericsson cycles are the two thermodynamic cycles that are used in power generation. While they both operate on similar principle, they are there are some key differences between them. The Stirling cycle is a closed cycle engine that uses fixed amounts of gas and operates by the cycle compression and expansion of the gas at different temperatures. The Ericsson cycle, on the other hand, is the open cycle engine that uses continuous flow of gas and operates by the isothermal compression and expansion of the gas. The main advantage of a Stirling cycle is the high efficiency, while the main advantage of the Ericsson cycle is its simplicity in case of maintenance. Here in the TS diagram, or in simply in PV diagram, we can see here are the both the, as we have seen in Carnot cycle, the heat addition and heat rejection are the isothermal processes, and here are the both are same, but instead of isentropic processes, here we using the constant volume processes, and in the Ericsson cycle we are using constant pressure processes. That is the key difference or evolution of Carnot cycle into Stirling and Ericsson cycle. Thank you.